All right, so hyperbolic functions. So section 3.11, we're going to look at what are hyperbolic functions, where are they coming from, what they are, and what are they, how are they related with trigonometric functions? Because, well, by the notation, you will find out that they look similar to the trigonometric functions because, well, you'll see why. So, to begin with, hyperbolic functions, from the algebraic point of view, they are combinations of e to the x and e to the negative x, all right? So they're combined. And, well, they are analogous to the trigonometric functions because of the following. Well, number one, so in trigonometry, you describe points around the unit circle. Well, of course, the circle doesn't have to be unit all the time, but for the sake of simplicity, we take the example of the unit circle, So, but the thing here is that these points describe these following order pairs of the form cos theta and sine theta, right? So the x-coordinate of the point around the circle describe the cosine function, and the y value, the y-coordinate described the sine function. All right. So in this case, well, in a similar way, hyperbolic functions. Well, that's why they are called hyperbolic, because these functions are not going to be described by the circle, but rather they're going to go. There are points that are going along a hyperbola. And, well, the notation for hyperbolic functions is very similar to the trigonometric functions, except that we add the letter h at the end of the name of the function, like cos x, sinh x. All right, so those are the differences and similarities. But now there's another difference here. Now, well, and notice I didn't write the symbol theta for the hyperbolic functions, and that's because we typically reserve the symbol theta, phi, alpha, beta, and gamma, and other letters from the Greek alphabet. We use them to describe angles, right? And that's what trigonometric functions are about, angles. And trigonometric functions have a very, very special property. That property that they are periodic. For example, if you're at any arbitrary point along this unit circle, or, well, this circle, if you add 360 degrees or 2 pi, don't we end up in the same point again? Yeah. So that's the property of periodicity of the trigonometric function. So we just go around in circles, in circles, in circles. However, that's not the case for hyperbolic functions. And in fact, well, we don't see that circular motion for the points that describe the hyperbola. So that's why in this case we're not using the theta symbol. Of course, if you want to use it just to make it look nice, well, that's fine. You can, when it comes to variables, you can put your favorite symbol, your favorite letter, that's fine. But just to be consistent with the distinction between angles and other kinds of values, well, we keep the x's here. And in fact, these points just go infinitely big or infinitely small. Do not go periodic. Do not repeat themselves after 2 pi units, So these are not angles. So those are the differences, So there's differences, there's similarities, that are important to consider when it comes to working with these functions. All right, so as mentioned before, these functions are combinations of exponential functions. So, for example, the sinh function is highlighted here. I'm going to highlight the two definitions that you need to know to derive the other remaining hyperbolic functions. All you need to know is these two functions, and in fact, they both look very similar. They are both They both contain e to the x. They both contain e to the negative x. However, the main difference here is that the sinh function has a negative sign in between, and the cosh function has a plus sign in between. So this will have a certain analytic implications that we're going to look in the next page. Well, you'll see. And well, coming back to the similarities between trigonometric functions and hyperbolic functions. So when we look at these identities here, I think these equations or these identities rather might ring a bell, right? Aren't they very similar to the trigonometric identities?
Yep.
What do we have? Well, tang, sinh over cosh, which is the same as the definition of the tangent function in the trigonometric without hyperbolic. Sine over cosine. Cotangent is the reciprocal of tangent, cosine over sine. Secant is the reciprocal of cosine, and cosecant is the reciprocal of sine. All we do is add the letter h for hyperbolic to describe a hyperbolic function. And of course, that changes the whole game because those functions, again, are not going to be describing angles, but rather these describe points along a hyperbolic, and these are exponential functions and not periodic functions like the trigonometric ones, right? So, okay, as a first exercise, how about we use these definitions of sinh and cosh to write the remaining four identities in terms of exponentials. Let's go ahead and do that. So let's start with the tang, because we already know what sinh and cosh is. So tang x, which is sinh over cosh. Well, so let's replace sinh and cosh with their corresponding definitions in terms of exponentials, the one which is in this case the ones I have highlighted here in the definition box. So let's go ahead, e to the x minus e to the negative x. Again, recall that the sinh function, the sinh function is the one that has a negative sign in between, and the cosh function is the one that has a plus sign in between. So from here, well, it might look a little bit funky. So, but in this case, all we can do is simply cancel out these 2's, and this is simply e to the x minus e to the negative x over e to the x plus e to the negative x. And that's how we define the hyperbolic tangent, but in this case, in terms of exponential functions based on the definitions of sinh and cosh. Right? Let's look at the next. Okay, let's put a check mark on this one. Let's look at the cosh function. And in this case, well, what do we have? Cosh. In this case, well, we don't need to write cosh over sinh. I mean, if you want to write it down, that's fine. But in this case, to save some work here, how about we just use the idea that the cotangent is the reciprocal of tangent. So using the result from before, just write down the reciprocal. That's our hyperbolic cotangent. So let's go ahead and do that. E to the x plus e to the negative x, e to the x minus e to the negative x. So we have one more. How about we write the last two? Sech x and cosech. Yeah, actually the pronunciation for is so it's sinh, cosh, tang. Those are easy to pronounce. But when it comes to the next one, cosh, it's kind of weird to pronounce. And then sech and cosech. I mean, those are like the shorthand name. But of course, if you want to name them hyperbolic sine, hyperbolic cosine, either way. Right? Well, the hyperbolic secant, sech, is only the reciprocal of cosh, which in this case is 2 over e to the x plus e to the negative x. And that's because, well, what do we have for cos? E to the x plus e to the negative x over 2. So just find the reciprocal. Just write the reciprocal. That's our sich function. Final answer. And for cosich, same, but with a minus in between. And there's really not that much to do here. So of course, I mean, that negative sign has some implications about having a complex fraction, but that's not what we're going to do at the moment. We will do it in subsequent examples. But in the meantime, are there any questions about what we have done so far? All right, so let's see. Let's move on to so for the next piece of information. Well, so again, like mentioned before, these functions sinh and cos are combinations of e to the x and e to the negative x. For example, I'm going to take as an example the sinh function. So sinh, which is e to the x minus e to the negative x over 2. This can be rewritten the following way: 1/2 e to the x minus 1/2 e to the negative x, which is a combination, which is where the combinations of the two functions are here together. And well, if we look at the two graphs together, these two graphs separately in a way give rise to the actual shape of the sinh function. And also the same happens with the cos function. So when we write, it's two separate parts in terms of the exponential function. They're graphed in here in a way. These two functions, the one in blue and the one in green, give rise to the shape of the actual of the graph of the actual cos function. All right, now let's have a look at these two graphs. So one of these two graphs represent an even function, and one of these two graphs represent an odd function. Can anyone point out which one is which?
I think the odd function's on the left.
On the left? Is it the odd?
Yeah, I think so.
And well, this one has to be the even, of course, right? There's no. Exactly, right? So there's a few ways to describe this evenness and oddness or the parity of the functions. So, well, because we're in the graphic point of view, yes, an odd function is a function that is, its graph is reflected about the origin. Well, in other words, if you grab this graph, you turn it 360 degrees and you end up with the same graph, then that is an odd function. But otherwise, when the function is even, its graph would be that of a symmetric about the y-axis. All right? So
if we fold it about the y-axis, it will come together.
Exactly. So you can think of the y-axis as a mirror. You know? That's exactly. You fold it and you get it this way pretty much. That is correct. All right, let's see what's next. So now that we described what hyperbolic functions are, where are they coming from, and how do we describe them? How are they related to trigonometric functions and what their main differences are? Well, how about we do some arithmetics with them? How do we evaluate functions? You know, for example, cos of 1, sinh of ln of 5, and yes, these numbers, especially letter B, might look a little bit funky, but trust me, it's not as bad as it initially looks. Well, the reason why we need to keep in mind the definitions in terms of exponential functions is because in many cases, calculators may not have built-in functions to compute hyperbolic functions. Some of them have, some others don't. But ultimately, the goal is to compute these calculations in terms of exponential functions. So let's go ahead and look at some examples. So, and again, I'm going to go back to recall what the cos function is. Cos x e to the x, e to the negative x, over 2, sinh e to the x, e to the negative x, over 2. This is minus, this is plus. Right? They both look the same, just the sign in between the exponentials in the numerator of this of each definition. So for cosh 1, well, just like any other function, you know, all we do is replace x with whatever value we have for x. In this case is 1. That's all we do. E to the first plus e to the negative 1 over 2. And in this case, well, let's see. E to the first power is simply e. E to the negative 1, you might want to rewrite it as 1 over e over 2. And well, in this case, this is a complex fraction that we still need to simplify. So when you do the homework, it might ask you to simplify it all the way. So yes, this is the preliminary result, but WebAssign may not accept this as a final answer. So or it might tell you, although your answer is correct, it's not written in the most simplified way, you know, so it might give you a dialog box like that. So what we need to do in this case is simplify this by multiplying numerator by and denominator by the least common denominator. Alright? Oh wait, no, that's not 2. It's actually e. How do we know that's the least common denominator? That's e over 1, that's 2 over 1, and we look for the overall least common denominator, yes?
You want it like that or separate fractions?
Do you mean these two separate fractions?
Yeah, like how this, you want it like that or separated?
We could separate it as well, but I mean, okay, yes, if we separate it, for example, what we could do is, okay, an alternative way is e over 2 plus 1/2 e to the negative 1, which is the same as e over 2 plus 1 over 2e. That's another way to rewrite it. Okay, and well, we want to combine these two fractions together, but we cannot just combine these fractions like this because we do not have a common denominator. We need to make sure that the two denominators are the same. So, well, this is a 2e. I need to multiply and divide by e on the first fraction, and only then we'll have a common denominator. We will be able to combine the two fractions together. So that's e squared plus 1 over 2e. And this is a simplified fraction whenever we don't have a complex fraction. That is when we have fractions over fractions, not like this. In this case, it's numerator denominator. All right. Are there any questions about this exercise? All right, let's move on to letter B. Sinh ln of 5. So again, we're going to recall the definition of the hyperbolic sign, which in this case is e to the x minus e to the negative x. So, well, so e and then minus e to the negative over 2, but in this case, ln of 5, ln of 5. And I know this expression looks big, looks funky. However, I think we can simplify this very nicely. Any ideas on what to do to simplify it?
Can you bring the ln5 to the front, or am I just not remembering the math correctly?
You're close. You're close.
You can cancel the natural log and
Yes, we can do that. So, do you mean e and ln canceling that like this?
yeah.
Can I do this as well?
Yes.
Yes. Mm-hmm.
The 5 is on the bottom. Multiply.
The 5 in the bottom.
1 to the negative 5. What is the negative number now?
So the negative is causing trouble here, right? We cannot just cancel this just yet. Well, of course, we can do the first. Okay, let's go ahead and do that. And so that's 5. That reduces to 5. And that's because of this rule. Let's actually recall what those rules are. Whenever we have e to the ln of x, these two cancel to give simply x. And the other way around, whenever we have ln of e to the x, that equals x. And well, this is something you learn either in intermediate algebra in high school or in pre-calculus, well, depending where you learn it. First, you learned it as a relation between two inverse functions. That is, that exponential function is the inverse of the natural log, and vice versa. So, and then you use that as a very powerful tool to solve exponential equations and logarithmic equations. So, but now we're going to use it to simplify expressions that involve this kinds of one. And of course, that you use it when you look at the L'Hopital's rule to compute some limits in Calc 1. And well, of course, we will keep using this powerful tool as well. And well, in this case, we cannot just cancel this e to the negative ln x. We need another property of logarithms. This one, a ln x equals ln of x to the a power. That is, the coefficient of the logarithmic function becomes the power of the argument. In this case, that expression inside is called the argument. Well, I have a name for that property. I usually call it the basketball smackdown rule, because well, whenever we do this, it's like doing basketball here. And when we do it the way around, that's the smackdown rule. Right? Depending one way or the other. Yeah, I think it's just a very cheesy way to remember this property. I mean, and well, in this case, we're going to use this property in one direction so we can simplify this. And in this case, we're going to use the basketball rule. What we're going to do is bring that negative coefficient as a power, because well, that ultimately that negative coefficient means a negative one, an invisible negative 1 as a coefficient, right? Because these properties right here work when the coefficients are 1. But if there's something else, we need to do some work first of all, which is what we're going to do here.
Can we also write e to the negative natural log 5 into 1 over into natural log?
That's another way we can do it, of course. There's many different ways to do that. So yes, that's an alternative. E to the ln of 5 to the negative 1. So that's what we're doing by using the basketball rule of logarithmic functions. All right? And over 2, and only then we can cancel e with ln. So that's going to be 5 minus 5 to the negative 1. I'm still going to leave it as 5 to the negative 1. Of course, this 5 to the negative 1 means 1 over 5, but I don't want to do everything in one shot. I'd rather show every single step here. So that's something I typically do when I'm lecturing. I try to show every single step, which is what your textbook doesn't do. You know, you read the textbook, oh, setup, okay, fine, and then one step and final answer, and they skip like 17 steps. Well, I'm going to do all steps, and sometimes what I like doing is go back and recall these basic properties from pre-calculus, from basic algebra, just to make sure we're all in the same page, so you don't miss anything. You know, I'm not going to assume like, oh, you should know this from pre-calculus. Oh, you should know. So I'm try to do all. Okay. So what's next? Okay, 5 to the negative 1. That's 5 minus 1/5 over 2. And well, what's 5 minus 1/5? One way to do this is 25 fifths minus 1/5. How many fifths is that? 24 fifths. Well, be careful here, because when it look at this fraction, these kinds of fractions might be a little bit misleading and ambiguous because when we read these fractions, it's not clear whether we are dividing 25/5 over 2 or 25 over 2/5, which are two totally different results. So my advice here, do a bolder division sign for the lowest fraction and add an invisible one. And do fraction over a fraction, so dividing by a fraction is, oops, it should say 24, right? 24 over 5 times 1/2 times the reciprocal of the fraction in the denominator. Well, in this case, we can divide out 24 over 2, which reduces evenly to 12, and 12 over 5. And that's our final answer for this. All right?
Can I write it down as 2.4?
Yeah, I mean decimals is fine. I mean ultimately this will depend on the instructions in our homework. It might ask you to. That's a good question actually. Thanks for pointing that out. So it might ask you to. We might ask you for an exact answer, which is an answer like this, or rounded to 2 or 3 or 4 decimals. So typically for functions that come from exponential, they are rounded to 3 or 4 decimals. All right? Okay, let's move on through example number 3. So we are going to work with algebraic expressions of sinh and cosh. We're going to write in this case their corresponding version in terms of exponential, because again, let's keep in mind that hyperbolic functions are functions of exponentials e to the x and e to the negative x. So let's go ahead and, okay, 7 sinh x plus 4 cosh x. All we have to do is simply replace sinh with whatever definition is and cosh with whatever definition is rather. So 7 e to the x e to the negative x over 2 plus 4 e to the x e to the negative x over 2. Sinh has the negative in between and cosh has the positive in between. Right? Again, that's a good way to remember those two identities. So you don't have to memorize the 6 of them. All you need to know is sinh is this definition and cosh is that definition, and to distinguish is the sign in between the exponential signs, the exponential terms rather. From there, the other 4 just come the same way we did it before. Okay, so let's distribute. That's 7/2 e to the x minus 7/2 e to the negative x plus 4 over 2. That's going to be reducing to 2 e to the x plus 2 e to the negative x. So to simplify this, let's just, whoops. I'm going to highlight the like terms so you can see what am I combining with. All right. So you can see the like terms and how are we going to combine them. Well, so the terms I highlighted in yellow are the ones that have the e to the x, e to the positive x. All we do is combine the coefficients. So 7/2 plus 2. I believe, okay, so that's 2 times 2 is 4 plus 7. What's 4 plus 7?
5.5.
So that's 11 halves e to the x and negative 3 halves, I believe it is, e to the negative x. And that's our final answer. So what we did is to write that function or that expression in terms of hyperbolics into that of a exponential version. All right? Yeah. Any questions about it? All right, let's move on to the next one. Okay, write sinh 3 ln x as a rational function of x. So it's going to be a similar exercise like part B from the previous page. And well, so sinh 3 ln x, this is the same as saying e to the minus 3 ln x, 3 ln x over 2. Can I do this?
Not yet.
Not just yet, right? So we need to take care of those coefficients. So in this case, we will do the basketball rule twice. That 3 will become the power of x, and that 3 will become the power of x along with the negative sign. Not just the 3, but also the negative 3. Don't forget the 2 in the denominator. And my advice here this time, to avoid those funky looking rational expressions, I'm going to rewrite this 2 in the denominator as a 1/2 coefficient. So in this case, well, this will become e to the ln of x cubed minus e to the ln of x to the negative 3. Okay? And only then we can cancel out e with ln by the inverse properties between exponentials and logarithmic functions, right? Again, it all stems from the same definitions, back and forth. So what are we going to be left with? Well, let's have a look. 1/2 x cubed minus x to the negative 3. I know we could have written it as 1 over x cubed. That's actually our next step. Because, well, yes, this looks okay as a preliminary final answer, but when you submit this on your homework on WebAssign, it might not ask for, it may not want this negative exponent. So number 1, that's 1/2 x cubed. I'm going to leave a space here, you'll see why. And that's minus 1 over x cubed. And well, that space I left on to the right of x cubed is to make this look like x cubed over 1, so we can combine the fractions together. So these are two fractions, but unfortunately these two fractions do not have the same denominator. Alright, they don't have the same denominator. We need to find a common denominator so we can put them together. So the LCD between 1 and x cubed, it would work if we multiply numerator and denominator by x cubed. And now that we have the same denominator, this will be 1/2. So that's x cubed times itself. What do we do with the exponent when we multiply the same base? Do we also multiply them? Do we add them? So that's x to the 6 minus 1 over x cubed. And we'll just bring down this 1/2 as the coefficient in the denominator, x to the 6 minus 1 over 2x cubed. And that's final answer. And yes, that's actually that's consistent with the purpose of the exercise, which is to write the composition between sinh and the logarithmic function in terms of a rational function of x. And this is a rational function by definition. Recall that the definition of a rational function is polynomial over polynomial. Yes, this might look like a rational function because, well, it's a quotient, right? But this is not a rational function because of the radical. So that's not in the category of rational functions. From pre-calculus, the definition of a rational function is polynomial over polynomial. All right? Coming back to the similarities and differences between hyperbolic functions and trigonometric functions, well, let's have a look at the first two. Sinh of negative x equals to negative sinh, and cos of negative x equals to cos x. Do these two identities right here kind of ring a bell from pre-calculus at all? What about it, if so? Yes, sir?
So instead of the sum of cosine squared plus sine squared equals 1, so here we have the differences of cos squared and sine squared, sine squared equals 1.
Okay, but I mean only these two identities right here, the first two. Yeah.
Because they're uneven functions.
Odd and even functions?
Yeah.
Yes, you're going to say that? Well, so it's the same oddness and evenness of function for the sine function and the cosine function. Recall the sine function, well, starts at the origin. It's perfectly symmetric about the origin, and the cosine function starts at 1, having like an upside down parabola between negative pi halves and pi halves. Well, that looks like it's an even function. And of course, okay, yes, let's write that down. This is the fact that f of negative x equals f of x. F of negative x equals f of x. All right? So that's the analytic criteria to distinguish between even functions and odd functions. So we did it before on the second page from the graphic point of view. You know, we had the graph of sinh and cos. One was symmetric about the origin, the other one was symmetric about the y-axis. You know, another funny name for this idea is, let me have the negative sign. It's the spit swallow property. So what happens with a odd function? So it actually spits the negative sign, but in an even function it swallows the negative. You don't see the negative sign anymore, right? So that's what happens with between even and odd functions, right? And well, that's another property that gets inherited from the trigonometric functions. There is another one, very, very interesting one right here. Cos squared minus sinh squared. It might look familiar from another trigonometric identity, right? So, and that is cosine theta quantity squared plus sine squared theta equals to 1. All right? And well, so those are some of the differences in the identity. So in some cases we have exactly the same identities as in the trigonometric, but in some cases we have similar identities in terms of just subtleties about like the order they were written because of the signs. All right? And in fact, the next example is to prove this identity. You know, like the same way you did it in trigonometry, you were given a funky looking identity, very complicated. Typically you worked it from the left hand side, use all the basic identities as a toolkit, and do algebraic manipulations to prove the right hand side. However, this will be when we finish this exercise, this will pretty much give us, or rather show us, the consistency of why these are called hyperbolic functions, what you will see. However, we're running out of time, and we're not going to do this in 5 minutes, and I don't want to rush through the problem, and I don't want to also get it halfway through the problem. So we're gonna take it from here next time.